Alkanes are saturated hydrocarbons. They are symmetrical molecules, their bonds are non-polar, and a great deal of energy is needed to break a bond. This makes alkanes very unreactive. Probably the most common reaction of the alkanes is combustion, and their use of fuels is very important. But there are two other important reactions we need to know about: the free radical substitution of alkanes and the cracking of long-chain alkanes. Let's look at the free radical substitution of alkanes. Methane reacts with chlorine to give a number of substitution products. The first substitution reaction results in the formation of chloromethane and hydrogen chloride gas. A carbon-hydrogen bond in methane has broken and a carbon-chlorine bond formed. Being a reaction between gases, it must take place in a sealed container. This means that further substitution can occur from the collision of a chlorine molecule with the first substitution product, chloromethane. The second substitution reaction results in the formation of dichloromethane and more hydrogen chloride gas. Two further substitution reactions occur, giving both trichloromethane and tetrachloromethane together with even more hydrogen chloride. If you're preparing the monosubstitution product chloromethane, what condition would ensure the best yield? Well, you just add excess methane. This would reduce the chance of collision between the chloromethane and more chlorine. In any event, the container is cooled to condense the mixture, and the desired product is then separated by fractional distillation. So let's look at what conditions are needed for this substitution to take place and how the reaction occurs. The energy required to break a chlorine-chlorine bond is within the energies present in ultraviolet light. So, to initiate the reaction, the reactant mixture is irradiated with UV light. In fact, the reaction is explosive in bright sunlight, but it doesn't take place at all in the dark. The chlorine radical formed is extremely reactive, and when it collides with the methane molecule, the following reaction occurs. The chlorine radical takes a hydrogen atom from a methane molecule to form hydrogen chloride. In doing this, the carbon-hydrogen bond in methane breaks homolytically, forming a methyl radical, CH3 dot. So why does this carbon-hydrogen bond break homolytically? Simply because the carbon-hydrogen bonds in methane are non-polar. These two steps are called propagation steps, and added together they give the overall reaction. The propagation steps are exothermic, and the chain reaction may be explosive. The final stage of the mechanism is called termination. It involves the combination of two free radicals to form a molecule, a chlorine radical combining with a methyl radical to form chloromethane, or two methyl radicals combining to give ethane, C2H6. The presence of a small quantity of ethane in the final product mixture is an indication of the validity of this reaction mechanism. Most of the alkanes we use come from crude oil or petroleum oil, that is a very complex mixture of hydrocarbons, mainly alkanes, that have been formed over millions of years by the action of high pressure and high temperature on sea creatures and plants which died and fell to the seabed. In the absence of air, they have been converted into oil and natural gas. Crude oil, because of its complexity, is of little use, but it can be separated into more useful fractions by fractional distillation. Fractional distillation of crude oil is carried out under reduced pressure in a process called vacuum distillation. Reducing the pressure lowers the boiling point, enabling the high boiling point fractions to be distilled over a lower temperature. We don't heat the crude oil to a temperature higher than 350 degrees Celsius to vaporize it, because it would thermally decompose at such high temperatures. Let's compare the fractions obtained from an oil refinery. As the tower is descended, the molecules are bigger. They contain more carbon atoms and the fractions become more viscous, meaning less runny. As the molecules increase in size, the van der Waals forces between them increase. This is why there is an increase in boiling point and viscosity. These boiling point fractions, although they are still complex mixtures, are more useful than the original crude oil. The lower boiling point fractions, which condense near the top of the tower, are used as fuels. They are easily ignited. They burn readily in air or oxygen with very exothermic reactions, and provided there is a plentiful supply of air, they burn with a clean flame. A clean flame is an indicator of complete combustion, and when these alkane fuels burn in an abundant supply of oxygen, they form carbon dioxide and water vapour only. With larger alkane molecules, more oxygen is needed for complete combustion. If we take undecane, C11H24 as an example, 17 moles of oxygen are needed for the complete combustion of undecane compared with just 5 moles for propane. So, the bigger molecule is more likely to undergo partial or incomplete combustion, producing unburned particles of carbon, carbon monoxide gas, and producing less heat. Carbon monoxide is a toxic gas causing death by oxygen starvation, and carbon is soot which causes smoke pollution. So, bigger molecules are less use as fuel. Petrol is the fuel used in the internal combustion engine of a motor car. Its main component has the molecular formula C8H18. And when it burns, it produces carbon dioxide and water. But it also produces sulfur dioxide, carbon monoxide, oxides of nitrogen, and unburned hydrocarbons. How are these pollutants formed when the petrol-air mixture is sparked and explodes? In the petrol are some sulfur-containing impurities, which burn in oxygen to form sulfur dioxide. On entering the atmosphere, the sulfur dioxide and some sulfur trioxide dissolves in rainwater to give acid rain. Carbon monoxide is also formed from the incomplete combustion of petrol, and oxides of nitrogen are formed from nitrogen in the air at the highest temperature in the cylinder of the engine. How are these pollutants removed from gaseous emissions from a motor vehicle? To minimise the emission of sulfur dioxide, most of the sulfur impurities are removed from the petrol itself, and low sulfur petrol is available at the petrol pumps. Other pollutants are removed by a catalytic converter present in the exhaust system. Catalytic converters contain catalysts such as platinum, palladium, or rhodium. As these are expensive metals, costs are reduced by the materials being thinly coated on a cheap ceramic. Car exhaust fumes are quickly removed through the exhaust, so the catalysts must be very efficient. How is it made efficient? The catalyst is made more efficient by its shape. The ceramic material is honeycomb in structure. This gives a greater surface area on which reactions can take place, speeding up the reactions. A catalytic converter removes up to 90% of the harmful gases. It enables the pollutants carbon monoxide and nitrogen monoxide to react, to form harmless carbon dioxide and nitrogen in a redox reaction. In another redox reaction, unburned hydrocarbons react with nitrogen monoxide, forming harmless carbon dioxide, nitrogen and water vapour. The proportion of each fraction in crude oil varies, and there is great demand for the lower boiling point fractions for use as fuels. In fact, there is a shortage of these shorter chain fractions, but there is a surplus of higher boiling point fractions. Larger alkane molecules are broken down into smaller molecules by a process known as cracking. Cracking can be carried out in two ways: thermal cracking and catalytic cracking. The products of the cracking reaction are different for each method. Thermal cracking requires a high temperature, a high pressure, and a very short exposure time. If the conditions are applied for too long, thermal decomposition takes place, resulting in the formation of separate atoms. Thermal cracking yields a high proportion of alkenes, which can then be converted into plastics. The higher the temperature, the greater the likelihood of carbon-carbon bonds breaking near the end of the alkane molecules, giving a high proportion of alkenes with low relative molecule masses. For example, ethene and propene. The thermal cracking reaction proceeds by a free radical mechanism. Carbon-carbon bonds are then broken homolytically, both fragments retaining one electron from the bonding pair. Here is an example of homolytic fission resulting in the formation of free radicals. Catalytic cracking uses much lower temperatures and pressures, but produces very different products. The conditions for catalytic cracking are a temperature of around 450 degrees Celsius, a slight excess of pressure, and a zeolite catalyst. Catalytic cracking produces mainly branched alkanes, cycloalkanes, and aromatic hydrocarbons. Very few alkene molecules are formed. These main products are used as motor fuels. Branched chain hydrocarbons are good as fuels as they prevent knocking, which is the pre-ignition of the fuel-air mixture before sparking. Catalytic cracking proceeds by a carbocation mechanism. A carbon-carbon bond breaks heterolytically, producing positive and negative ions. One fragment retains both bonding pairs of electrons, the other none. Here is an example of heterolytic fission. The positive ion formed is known as a carbocation.
Alkenes are unsaturated hydrocarbons containing a carbon-carbon double bond. This double bond has a high electron density, and the chemistry of the alkenes is characterized by electrophilic addition reactions. They are very useful as they can readily be converted to other compounds. The simplest alkene is ethene, C2H4. Let's look at the structure of ethene. Because they are unsaturated, alkenes undergo addition reactions where two molecules add together to form one. They will react with hydrogen gas to form alkanes. For example, ethene reacts to give ethane, C2H6. The conditions required for this reaction are a temperature of 150 degrees C and a finely divided nickel catalyst. The catalyst is finely divided to provide a large surface area on which the reaction can take place, and the process is known as catalytic hydrogenation. This is used in the manufacture of margarine, which is actually made from vegetable oils. Vegetable oils are liquids containing mainly unsaturated compounds, and partial, controlled catalytic hydrogenation causes some saturation and a hardening of the margarine. So why not complete hydrogenation of the margarine? Because the resultant margarine would be too hard, and polysaturates are not good for our health. The double bond in alkenes can be viewed in a different way. Let's look at it as if each carbon atom in ethene has 3 bonds, 1 carbon-carbon and 2 carbon-hydrogen. Looked at it like this, we can see that the shape of the molecule is planar, with bond angles of 120 degrees. We know that a carbon atom has 4 electrons in the outer shell, but it is forming only 3 bonds. So each carbon atom must have a spare electron, and these spare electrons are in p orbitals. The sideways overlap of the p orbitals means that there is electron density above and below the carbon-carbon bond. This region of high electron density makes alkenes susceptible to attack by an electrophile. But what is an electrophile? An electrophile is a positive ion or an electron-deficient atom that seeks an electron-rich site. It forms a bond by accepting a lone pair of electrons. Alkenes react with bromine water in an electrophilic addition reaction. For example, propene reacts to give 1,2-dibromopropane. But what about the mechanism for this reaction? As the bromine molecule approaches the propene molecule, The negative charge density of the pi bonding in propene induces a slightly positive charge on the bromine atom which is closer to the alkene. The bromine-bromine bond breaks heterolytically, forming a bromide ion. The other bromine atom accepts a pair of electrons from the carbon-carbon double bond, bonding to a carbon atom. The carbon-carbon double bond becomes a single bond. The intermediate in this reaction is a carbocation. The lone pair of electrons on the bromide ion is donated to the positive carbon atom of the carbocation to form a second carbon-bromine bond. In this reaction, the electrophile is the electron-deficient delta-positive bromine atom of the bromine molecule. This is an addition reaction, initiated by an electrophile. So, the mechanism is called electrophilic addition. In mechanisms, the arrows indicate the movement of electrons. When you draw reaction mechanisms, take great care where the arrow starts and where the arrow finishes. In the reaction with bromine, the electron density in the double bond induces a dipole in the bromine molecule. In the reaction with hydrogen halides, the attacking molecule has a permanent dipole, and alkenes will react with hydrogen halides to give a haloalkane. For example, ethene reacts with hydrogen bromide to give bromoethane. The reactants are either in the gaseous phase, or ethene is passed through concentrated hydrobromic acid. The hydrogen bromide adds across the carbon-carbon double bond. Once again, the mechanism is electrophilic addition. Alkenes can be converted into alcohols in the laboratory by a two-stage process. Let's look at ethene. First, it is reacted with cold, concentrated sulfuric acid to form ethyl hydrogen sulfate. Water is then added to the product and the mixture warmed. The water dilutes the excess acid and acidic hydrolysis takes place, forming ethanol. The overall equation can be obtained by adding the two equations together. Notice that sulfuric acid does not appear in the overall equation. Why not? Simply because it is acting as a catalyst. A molecule of sulfuric acid has this structure. And here is the mechanism for the first stage, the formation of the hydrogen sulfate. The delta plus hydrogen of the sulfuric acid is the electrophile, and the hydrogen sulfate ion has this structure. Ethanol is manufactured in the chemical industry by the direct hydration of ethene, but the conditions required are not suitable for laboratory preparation. When hydrogen bromide, or concentrated sulfuric acid, followed by acid hydrolysis, is reacted with propene, there are two possible products. The hydrogen atom can bond with carbon 1, or it could bond with carbon 2. In both cases, both addition products are formed, but one isomer will be in excess. In order to explain which isomer and why, we need to examine the two possible mechanisms. Let's use the addition of hydrogen bromide as the example. The explanation lies in the difference between the two carbocations formed at the first stage of the mechanism. This secondary carbocation is more stable than this primary carbocation, and a more stable carbocation is more likely to be formed. So, this is the major product. What about a tertiary carbocation? It is more stable still, as it has 3 alkyl groups attached. When 2-methylbutene reacts with hydrogen bromide, the major product is 2-bromo-2-methylbutane. The tertiary carbocation is more stable than the secondary carbocation. But if the alkene is symmetrical, there is only one product. Reaction of butene with concentrated sulfuric acid, followed by acid hydrolysis, gives the one product, butantuol. A very important feature of the chemistry of alkenes is that they can undergo self-addition to form addition polymers. Addition polymerization involves many alkyl monomer units adding together in a chain to form one polymer molecule. The equation which illustrates the polymerization of chloroethene to form the polymer polychloroethene is... What equation shows the polymerization of propene? Be careful. Although the monomer is an unsaturated molecule, the polymer is saturated. Another important chemical manufactured from ethene is epoxyethane, a cyclic ether. It is produced by the partial oxidation of ethene with air, or oxygen. And the conditions used to do this are a temperature of 250 to 300 degrees C, a pressure of 1 to 2 megapascals, and a silver-based catalyst. The main impurities are carbon dioxide and water from the complete combustion of ethane. A little 1,2-dichloroethane is added to act as an oxidation inhibitor and reduce complete combustion. Care must be taken during the manufacturing process because epoxyethane is very unstable and explosive, flammable, highly toxic, can cause irritation of the respiratory system, and can have an adverse effect on the nervous system. Not very nice. The epoxyethane produced must be purified by fractional distillation. It is a colourless gas that boils at 10 degrees C and can be used as a sterilising agent. Epoxyethane is very unstable because it has a strained three-membered ring structure. We know that each carbon atom normally has 4 covalent bonds, which would be arranged tetrahedrally with bond angles of 109.5 degrees. In epoxyethane, the carbon atom has bond angles of only 60 degrees. As a result, it readily reacts with nucleophiles, such as water, in reactions that are exothermic and involve breaking a CO bond, opening the ring. Epoxyethane reacts with water to form ethane 1,2-diol, another important product. In industry, sulfuric acid is added as a catalyst. A temperature of 60 degrees C is used, as the reaction with cold water is only slow and a 10-fold molar excess of water is used. After evaporation to concentrate the ethane 1,2-diol, it is separated by fractional distillation. Ethane 1,2-diol is used in the manufacture of and the manufacture of non-ionic surfactants present in detergents. It is also used as antifreeze in cars, for which it is ideal as it has a low freezing point, minus 12 degrees C, has a high boiling point, 198 degrees C, and it is completely miscible with water. Ethane 1,2-diol can react with epoxyethane. If less water is used in the process, ring opening of more epoxyethane molecules can occur with the formation of polymer molecules, polyethylene glycols. Haloalkanes and alcohols. The functional group in haloalkanes, or halogenoalkanes as they are also called, is a halogen atom. They are named with the term halo as a prefix. For example, chloro, bromo, etc. As halogens are more electronegative than carbon, the carbon-halogen bond is polar, and the carbon has a delta-positive charge. This makes haloalkanes very reactive, as the delta-positive carbon atom is susceptible to attack from a nucleophile. A nucleophile is the opposite from an electrophile. It is a negative ion or electron-rich molecule which seeks an electron-deficient site. It provides a lone pair of electrons for bonding. Aqueous hydroxide ions are powerful nucleophiles, and haloalkanes react readily with aqueous hydroxide ions. The haloalkane is warmed with aqueous sodium hydroxide or potassium hydroxide. Chloroethane reacts with sodium hydroxide solution to form ethanol. Here is the mechanism for the reaction. As the reaction involves substitution and the initial attack was by a nucleophile, the reaction is a nucleophilic substitution. There are 2 factors that might influence the rate at which a haloalkane undergoes nucleophilic substitution: the strength of the dipole and the strength of the covalent bond. Here are tables which indicate those values for haloalkanes of butane. If the strength of the dipole is the most important factor, then 1-chlorobutane, having the strongest dipole, would be the most reactive. If bond strength is the deciding factor, 1-iodobutane, having the weakest bond energy, would be the most reactive. Actually, 1-iodobutane is the most reactive, 1-bromobutane the next, and 1-chlorobutane the least. So, the relative strengths of the carbon-halogen bond is the most important factor. Haloalkanes react with the nucleophile Cn-, the cyanide ion. This reaction is very useful as it increases the carbon chain length. The haloalkane is warmed with sodium cyanide or potassium cyanide, dissolved in a mixture of ethanol and water. 1-bromopropane reacts with aqueous ethanolic potassium cyanide to give butane nitrile. Note that the organic product has one extra carbon atom compared to the reactant. Here is the mechanism for the reaction. The ammonia molecule contains a lone pair of electrons and can act as a nucleophile, so haloalkanes react with ammonia. Bromomethane reacts if it is warmed with excess ammonia in a sealed container. Let's look at the mechanism first this time. Note that the ammonia molecule provides a lone pair of electrons for an electron-deficient site, so it is behaving as a nucleophile. The second stage of the mechanism is as follows. Notice that in this case, the ammonia molecule is acting as a base. By adding the two stages of the reaction together, we obtain the overall reaction. The type of organic molecule formed is called an amine, in this case, methylamine. Excess ammonia is used to reduce the formation of further substitution products, as the amine can react with more bromomethane molecules to form secondary and tertiary amines. If a haloalkane is reacted with a hot solution of sodium or potassium hydroxide and ethanol, an alkene is formed, as well as an alcohol. 2-bromopropane reacts to form propene. Here is the mechanism. The role of the hydroxide ion in this mechanism is to act as a base. It accepts a proton, H+. In this reaction, a molecule of hydrogen bromide has been eliminated from the haloalkane and a carbon-carbon double bond has been formed. So we describe this mechanism as elimination. Reaction between 2-bromobutane and hot ethanolic sodium hydroxide yields 2 alkenes. In the reaction between hydroxide ions and haloalkanes, both substitution and elimination will occur, but the proportion of alcohol to alkene depends on the conditions used. An aqueous solution favours substitution. An ethanolic solution favours elimination. The higher the temperature and the stronger the base, the more the likelihood of elimination. Primary haloalkanes favour substitution, whereas tertiary haloalkanes favour elimination. With secondary haloalkanes, there is no preference. Both substitution and elimination occur equally at the same time. Alcohols contain the functional group OH, called the hydroxyl group. An open bottle of wine left exposed to the air turns to vinegar, as the alcohol it contains is oxidized to carboxylic acids. The products from the oxidation of alcohols depends on the type of alcohol, whether it is a primary, secondary or tertiary alcohol. The oxidizing agent normally used is hot acidified potassium dichromate 6. With primary alcohols, there are 2 products dependent on the conditions. It is first oxidized to an aldehyde. Let's use propan-1-ol as an example. Further oxidation of the aldehyde can take place to form the carboxylic acid. Here, the oxidizing agent converts the CH to COH. As there are 2 possible products, how can we ensure we produce the product we want? Okay, if propanal is the desired product, it has a boiling point of 322 Kelvin, which is lower than both propan-1-ol, 371 Kelvin, and propanoic acid, 414 Kelvin. So it is allowed to distill off as soon as it is formed and before it can be further oxidized to propanoic acid. If propanoic acid is the desired product, the mixture can be heated under reflux. The vertical condenser condenses the volatile propanol, which falls back into the distillation flask and is further oxidized to propanoic acid. If a secondary alcohol is oxidized, it forms a ketone. If we look at propan-2-ol as an example, this is exactly the same as the first stage oxidation of the primary alcohol, but there isn't a second stage. Because there is no CH bond on the ketone, COH cannot be formed, and the oxidizing agent cannot break the CC bond to form COC, so there is no further reaction. Tertiary alcohols cannot be oxidized, because there is no hydrogen atom on the carbon of the COH bond, so two hydrogen atoms cannot be removed across the CO bond. The oxidation reaction can be used to identify tertiary alcohols from primary and secondary. When the orange dichromate 6 ion acts as an oxidizing agent, it is reduced to the green chromium 3 ion. When primary and secondary alcohols are heated with acidified potassium dichromate 6 ions, the colour changes from orange to green. With a tertiary alcohol, the orange colour stays. It is not so easy to distinguish between primary and secondary alcohols. Firstly, their oxidation products from the reaction with acidified dichromate 6 have to be isolated by fractional distillation. Then these products are reacted with either Fehling solution or Tollens reagent. Both of these are mild oxidizing reagents, and both reactions need heating. Here are the results. We don't use acidified potassium dichromate 6 as the oxidizing agent in this test, as it is a powerful oxidizing agent and may cause carbon-carbon bond breaking in the ketone. The removal of water from alcohol molecules forms alkenes in a dehydration reaction. We have to use concentrated sulfuric acid or concentrated phosphoric acid heated to a temperature of 180 degrees C. Let's use propan-2-ol as the example. Notice that the acid doesn't appear in the equation. This is because the concentrated acid is a catalyst for the reaction. This is another example of an elimination reaction. Water is eliminated across adjacent carbon atoms and propene is formed. What is formed when butan-2-ol is heated with concentrated sulfuric acid? Ethanol is manufactured by two different processes, the direct hydration of ethene and the fermentation of sugars. Let's look at the direct hydration of ethene. A temperature of 300 degrees C and pressure of 6,500 kilopascals is needed, with phosphoric acid as a catalyst. Fermentation of glucose is shown by the following equation. Yeast and a much lower temperature of around 35 degrees C is used. Why 35 degrees C? Because below this temperature, the enzymes in yeast are relatively inactive, and at temperatures above 45 degrees C, they are denatured and ineffective. Of the two methods, which is the best depends on the end use of the alcohol. As far as costs are concerned, direct hydration is much faster and more cost-effective. It is a continuous process and cheaper in manpower compared with fermentation, which is a batch process. However, it does require more expensive equipment because of the high pressure involved. As far as raw materials are concerned, fermentation is preferable because sugar is renewable and the oil from which ethane comes is a finite source. But the ethanol obtained from direct hydration is pure, whereas the ethanol obtained from fermentation is impure and has to be separated by fractional distillation. But the ethanol manufactured by the two processes has different uses. Ethanol from fermentation is used in the manufacture of alcoholic drinks, and that from direct hydration is used in industry, for example, as a solvent.